In this presentation, we'd like to add some additional features or capability to our binary tree example. One that we'd like to be able to do is to get the maximum depth of the tree. So in these examples here, we can see that if we define the depth of an empty tree to be 0, where the root node is null, then that tree would be 0. The depth of that tree would be 0. Then these examples here would have a depth of 1, 2, 3. So the maximum depth is 3 levels deep on both of these trees. And before we get to that, it would also be nice to be able to visualize the trees. The challenge with that is that on our console, we can only print out text left to right, top to bottom. So it makes it difficult without any type of graphics capability to print out the circles and the connecting lines. But maybe we could print the information in a slightly different way so that we can kind of see the structure of the tree and the relationship between the parent and the child nodes. How could we do that? Here's an image of this example that we have here, and if we were to rotate this tree counterclockwise 90 degrees, we would end up with something like this. And then on our console, what we could do is print out the values of this binary tree that is sorted. We print out those values in reverse so that we'd start with the 25 on top and indent from left to right based on the depth that that node is at. So for example, the 25, since it's at the third level, we may indent twice and print out the 25. And then the 20 is at the second level, so we can indent just once. And then the 16 is at the third level. The root node 15 is at the top level, so we may not indent at all. And then the 12 is indented twice. And then the 10 is indented just one level. And then the 8 is indented 2 levels. So if you tilt your head sideways, you can kind of see the structure of the tree and the parent-child relationships. How could we do this? Unfortunately, this printing out in this reverse order isn't in any of our previous traversals. So the in-order traversal would get us bottom to top. So what we really need is the opposite of the in-order traversal. Maybe we'll call it a reverse order traversal. And instead of doing left node right, we would do right node left. So we'd start out by printing the right subtree and then print out the current node and then print out the left subtree at each recursive step. Let's see how we might add this to our existing sample code. This is our sample binary tree code that we've seen. Each tree node has an integer for information and then a left and right subtree. And we have the capability to ask if the tree is empty, display it, but this display is just displaying it as a list. It doesn't tell us anything about the structure or the internal structure of the tree. We can search for a value, we can add a value, we can get the smallest value, and then we can deallocate the memory, clear up the tree. So let's see if we can print this tree out sideways, and we'll call it display or print sideways. We know it's going to be recursive, so we make two versions of it. One, a public interface that's not recursive, and then the other that is the private recursive version that's going to take a tree node. I like to put the variable name in the header file, and then also it's going to take the current indentation level, which is going to be a constant string reference. And in order to use string, we have to include the string header and say that we're going to use namespace standard. So then we need to define these functions, print sideways and the public recursive version. Sorry, the private recursive version. This is the public non-recursive version that would be exposed outside of the class. And as we've seen in the past, all it does is call or invoke the public non-recursive version just calls or invokes the private version. And we're going to pass in the root of the tree and the current indentation level. So at the root of the tree there is no indentation, so we're just going to pass in an empty string. That's the current indentation level. Now we need to define the private recursive version. And the stopping case is whenever we reach a either root node or left or right node that is null, we don't want to do anything. So we only want to do something if P is not null. And what we want to do is print out the tree in a reverse order. So we want to print out the right part of the tree and then the current node and then the left part of the tree. And the left and right part of the tree will be printed out in a recursive manner by making a recursive function call. So to do the right part first, we'll call print sideways and pass in the current node's right pointer and then the new indentation level, which is going to be the current indentation level, and we'll concatenate some additional space to that. Then we will print out the current node but before we print out the current node we want to print out whatever spacing, whatever indentation we need. So we'll print out the indentation and then the current node's value and then a return. So we print out whatever indentation that we need and then the current node's value and then a return to go to the next line. So we've printed out the right subtree, we've printed out the current node's information, and now we need to print out the left subtree. And that's just a call to print sideways P left with the updated indentation level. So let's just do a quick build and see if that compiles okay. It seems like it's okay. So now in main we want to call this print sideways. This section of code here in main is testing the search capabilities, so I'll just comment that out for now. Put an output by calling the tree's public print sideways method. So let's see if this works. So here is our tree printed out sideways, and because we're putting in random values in the tree, we don't get a particularly well balanced tree, but we should still be able to see what the structure is. So if we take a screen capture of this and crop out the tree part, and then rotate it so that the root node is on top, and then we could paste this into some drawing program like Paint or something. We'll blow it up a little bit, and then we can fill in lines to see the structure. So here's the root node, and there's its right, and there's its left, and this is the left here, and this is the right here. Left, left. So you can see that 14 has a 6 on the left, and that 6 has a 14 on the right, and that has a 12 on the left, that has a 7 on the left, and a 14 on the right. So that if we were to print this in order, we would get the output that we see here, the list output that we see here, 2, 4, 6, 7, 12, and then we get a few 14s, and then a 16 and an 18. So this is kind of a nice way of displaying the tree that's not really pretty or elegant, but if you turn your head sideways you can kind of see the structure of the tree, and if you crop out a screen capture of this and rotate it, and you can actually put in the left and right node pointers and see the structure of the tree a little bit easier. So now that we have this, we'd like to be able to print out the maximum depth of the tree. And in this particular case, the maximum depth of the tree at the root node is 1 plus the maximum of the depth of the right subtree, or the larger of the right subtree or the left subtree. So in this particular case, this is the first level, and then this is the second level, and then this is the third level, and this is the fourth level, and this is the fifth level. So the height of this tree would be 5. The height of the right subtree at 14 is only 2, so if we count on the right side we'd only get 3, but on the left side we get 1, 2, 3, 4. So the recursive call is going to be, there's going to be 2 recursive calls. It's going to be the height of the left side, the height of the right side, take the larger of those 2 values and add 1 to account for the current level that we're at. And then the stopping case for the recursive depth call is going to be if the root node, or if the current node that we're at is null, we'll just return 0. We define a tree or a subtree with a null root as having 0 depth. So let's see what that might look like in the code. Again, we need 2 versions of it, the public non-recursive version, and it's going to return an integer, and then we need the private recursive version, and it will also return an integer, but we'll pass in the current pointer, the pointer to the current subtree that we're working on. So now the public non-recursive version, as we've seen before, is just going to call the private recursive version and get things started. So just call it. This recursive version is going to return an integer, and then we need to pass it through the call in this function by just putting a return statement here. So now we need to define a private recursive version. And my preference is often to do the stopping case first, so if p is equal to null, if p equals null, then we define that tree to be of 0 depth. So we just put a return 0. So if the root node is null, then that tree has a 0 depth. If the current subtree that we're dealing with, p, is null, then we return a 0 value. Else, we're ready for the recursive calls, and we want to return the current level, which adds 1 to the depth, plus the larger of these two values, depth of root left or depth of root right. So how do we get the larger of those two values? In C++, they have a function, it's a fairly common function called max, which gives you the maximum of two values. So what we do is we get the depth of the left subtree recursively, we get the depth of the right subtree recursively, and then the max function will give us the larger of those two values. Now we're getting an error message here because max isn't defined, so we need to add an additional include, and in this case max is defined in an include called algorithm. So again, the recursive depth call, we initially pass in the root node, and if it's null we return 0, otherwise we return 1 plus the larger of the depth of the left subtree or the depth of the right subtree. So now in main we can call this function by just calling the public non-recursive version of the function. And that will return the integer depth, and we'll just send that to the output, send it to cout. So let's see if this will build and run. So we have an exception here, Stack Overflow exception. That's curious. What did we do wrong? So let's step through in the debugger and see. Well, it looks like what we have here is an infinite recursion, which is curious. So let's see what we may have done wrong. From main, we're calling BST depth. So let's put a breakpoint in here. And here we're calling the recursive version So here we're calling the recursive version on the root node. So we'll step through this in the debugger, and the root node is has a value of 0, and everything is to the right of that one in this particular case. So we'll step in here, and the root node was not null. Now the root left so the root node is 6, and then the left is null. So if we step into the left, it is okay, so it looks like it's actually stepped into the right one from the parent first. And then the right, so the current node is 14, and then the right of that is 16. So if we step into this again, so we're stepping into these recursive calls. I see the problem. Okay, so the problem here, I accidentally made the recursive call with the root over and over again rather than with the current node P. So that was a logical error on my part. So that is going to cause us to just infinitely call root right, root right, root right, rather than P right and step down the tree. So let me stop the debugger, and we'll rebuild and try it again. So I'm going to take the breakpoint out and continue running the program. Seem to stop it. Let's try it again. So here is the program running here, and you can see the values printed out in the list and the values printed out sideways. So you can see here that 12 is the root node, and then the left of that is a 9, and the left of that is a 5, and the left of that is a 0, and then the right of that is another 5, and then a 2, and then a 2. So here we're getting a depth of 7. 1, 2, 3, 4, 5, 6, 7. So it looks like it might be working. Let's run it again. We'll have since we're seeding the random number generator, we'll get a different tree every time. So here we're getting a depth of 8. So there's the root node. 1, 2, 3, 4, 5, 6, 7, 8 levels of depth. So in this presentation we saw how we can add features to print the binary tree in a sideways manner so that we can somewhat see the structure and the parent-child relationship between the nodes, and also how to find the maximum depth of the tree. And these are good examples of adding additional recursive functionality to a tree.